In 1915, Albert Einstein published his theory of general relativity, revealing that massive objects literally warp the fabric of spacetime. But even Einstein couldn't fully grasp the implications of his own equations. When Carl Schwarzschild solved Einstein's field equations just months later, he discovered something that defied comprehension: regions where time dilation approaches infinity, creating temporal prisons where a single moment stretches toward eternity. To understand this mind-bending reality, imagine watching someone fall into a black hole. As they approach the event horizon, you would see them slow down, their movements becoming increasingly sluggish until they appear frozen in time forever. Meanwhile, from their perspective, they experience everything normally, falling through the event horizon in finite time while witnessing the entire future history of the universe unfold behind them in moments. Tonight, we're going to explore the most extreme time dilation effects in the universe. You'll discover why approaching a black hole transforms seconds into eternities, how infinite gravitational fields create temporal impossibilities, and what happens to time itself when space-time curvature becomes extreme beyond imagination. But hear us, what makes this truly disturbing? The mathematics of general relativity predict that time doesn't just slow down near black holes. It approaches complete stoppage. At the event horizon of a solar mass black hole, gravitational time dilation reaches factors exceeding YD, meaning a single second experienced by a distant observer corresponds to trillions of years near the black hole's surface. Dr. Kip Thorne from Caltech Nobel laureate, whose work confirmed gravitational waves, explains that black holes represent the most extreme manifestation of Einstein's spacetime, regions where the familiar concepts of space and time break down, completely revealing the universe's capacity for temporal impossibilities that challenge our fundamental understanding of causality itself. The numbers alone are staggering. Sagittarius A*, the supermassive black hole at our galaxy's center, containing 4 million solar masses, creates gravitational fields so intense that time flows 30% slower at its event horizon compared to Earth. For stellar mass black holes formed from collapsed stars, time dilation effects become incomprehensibly extreme, approaching mathematical infinity at the Schwarzschild radius. What makes this revelation particularly unsettling is the realization that black holes create temporal boundaries in spacetime itself. The event horizon represents not just a point of no return for matter and energy, but a temporal prison where the flow of time becomes so distorted that cause and effect relationships begin to break down according to external observers. As you read these words right now, black holes throughout the universe are demonstrating physics where time becomes infinitely stretched, where individual moments expand into cosmic epochs, and where the boundary between finite time and eternity blurs into mathematical abstractions that challenge human comprehension. The story of black hole time dilation is ultimately the story of spacetime itself, how mass and energy curve the very fabric of reality to create regions where temporal flow approaches zero while maintaining mathematical consistency with general relativity's field equations. If you're fascinated by physics that defies everyday experience, subscribe and hit the thumbs up button. And here is a question that will haunt your thoughts. If time approaches infinite dilation at black hole event horizons, what does that mean for information and consciousness trapped within these temporal prisons? Comment below with your theories. I'll pin the most thought-provoking response. Throughout this exploration, we'll uncover exactly why massive objects can bend time toward infinity, how Einstein's equations predict temporal impossibilities, and what black hole time dilation reveals about the fundamental nature of spacetime geometry itself. Now let's begin our journey into the physics of infinite time dilation, where seconds become eternities and mathematical infinity meets physical reality. Chapter 1. Time's prison time, the most fundamental dimension of human experience, becomes a prison near black holes where gravitational fields grow so intense they can stretch individual moments into cosmic eternities. The concept of time dilation near massive objects represents one of Einstein's most counterintuitive predictions. Yet decades of experimental verification have confirmed that gravity literally slows the passage of time itself. The foundation of time dilation lies in Einstein's equivalence principle, which states that gravitational acceleration and mechanical acceleration are fundamentally indistinguishable. When you accelerate in a car, you feel pressed back into your seat by a force that mimics gravity. Einstein realized this equivalence runs deeper. Acceleration through spacetime affects the flow of time itself, with stronger gravitational fields producing more dramatic temporal effects. Dr. Arthur Eddington, whose 1919 eclipse observations first confirmed Einstein's theory, described gravitational time dilation as the universe's most elegant demonstration that time is not the absolute, universal constant Newton imagined, but a flexible dimension that responds to the presence of mass and energy like a cosmic symphony, where gravity conducts the tempo of temporal flow. The mathematics begin with the Schwarzschild metric, the solution to Einstein's field equations for spherically symmetric, non-rotating masses. This metric reveals how spacetime curvature around massive objects affects both spatial distances and temporal intervals. For a clock positioned at distance r from a black hole of mass m, the gravitational time dilation factor becomes t underscore observed equals t underscore proper times square root 1 2 gm rc, where g represents Newton's gravitational constant, c the speed of light, and the denominator approaches 0 as r approaches the Schwarzschild radius rc equals 2 gm per c squared. This mathematical relationship reveals that time dilation becomes infinite at the event horizon itself. The physical interpretation creates a temporal paradox that challenges human intuition. From the perspective of a distant observer watching someone fall toward a black hole, the falling person appears to slow down dramatically as they approach the event horizon. Their clock runs increasingly slowly compared to the observer's reference frame, until at the exact moment they reach the Schwarzschild radius, they appear frozen in time forever. Dr. Leonard Susskind from Stanford University, whose work addresses black hole thermodynamics, explains that the event horizon represents a temporal boundary where the flow of time, as measured by distant observers, approaches complete stoppage. This creates what physicists call the frozen star solution images of matter, eternally suspended at the black hole as surface, never quite crossing the event horizon from an external perspective. However, the infalling observer experiences something completely different. From their reference frame, time flows normally as they pass through the event horizon and continue falling toward the central singularity. They experience no dramatic slowing of time, no moment of infinite duration. Their watch continues ticking at its normal rate throughout their journey into the black hole's interior. This dual perspective creates one of general relativity's most profound puzzles. The same physical event, crossing the event horizon, appears completely different to different observers. The distant observer sees eternal suspension, while the infalling observer experiences finite normal passage of time. Both perspectives are equally valid within their respective reference frames. The extreme case occurs at the event horizon of stellar mass black holes, where gravitational time dilation reaches factors that strain mathematical representation. For a black hole containing 10 solar masses, the Schwarzschild radius equals approximately 30 kilometers. At this distance, time dilation becomes infinite according to distant observers, creating a temporal prison where moments stretch toward eternity. Consider the implications for communication. Radio signals transmitted from near a black hole's event horizon become increasingly redshifted and time-dilated, as viewed by distant observers. A 1-second radio pulse transmitted from just above the event horizon would appear to last millions of years to external observers, gradually fading to undetectable intensities as the signal becomes stretched across cosmic time. The tidal effects compound the temporal imprisonment. Stellar mass black holes create such extreme tidal gradients that any extended object approaching the event horizon experiences spaghettification, stretching along the radial direction while being compressed in the tangential directions. These tidal forces become infinite at the event horizon, adding physical impossibility to temporal paradox. Dr. Saul Tucholsky from Cornell University, whose research addresses black hole perturbations and stability, notes that the combination of infinite time dilation and infinite tidal forces at the event horizon creates boundary conditions where classical general relativity reaches its limits. These mathematical infinities suggest that quantum gravitational effects, currently beyond our theoretical understanding, become essential near black hole horizons. The observational evidence for extreme time dilation comes from studying matter falling into black holes. X-ray observations of accretion disks around black hole candidates reveal spectral lines to become increasingly redshifted as matter approaches the event horizon. These observations confirm that time dilation effects approach the extreme values predicted by general relativity. The GPS satellite system provides everyday confirmation of gravitational time dilation on much smaller scales. GPS satellites orbit Earth at altitudes where gravitational fields are weaker than at Earth's surface, causing their onboard clocks to run approximately 38 microseconds per day faster than identical clocks on the ground. Without corrections for this time dilation, GPS accuracy would degrade by several kilometers per day. The philosophical implications of time as prison near black holes challenge fundamental assumptions about the nature of temporal flow. If time can be dilated to infinity, what does this mean for causality, free will, and the relationship between past, present, and future? The mathematical framework of general relativity provides precise descriptions of these effects while raising profound questions about the nature of time itself. The event horizon represents not just a boundary in space, but a temporal boundary where the normal sequence of cause and effect becomes ambiguous. Events occurring at the event horizon appear to take infinite time from external perspectives, yet occur in finite time for infalling observers. This dual nature suggests that time itself may be more complex than our everyday experience suggests. The energy requirements for escape provide another perspective on temporal imprisonment. The escape velocity at a black hole's event horizon equals the speed of light, meaning that even photons cannot escape once they cross this boundary. This creates a temporal prison not just for matter, but for information itself, leading to paradoxes about information conservation and the fundamental nature of physical law. As we delve deeper into the mathematics of spacetime curvature, we'll discover how Einstein's field equations predict even more extreme temporal effects, including regions where time curves back on itself and mathematical infinities become physical realities that challenge our understanding of what it means for time to flow in the first place. Chapter 2. Infinite Curves. Einstein's field equations reveal that spacetime near black holes doesn't just bend, it curves toward mathematical infinity, creating geometric impossibilities where the familiar concepts of distance and duration break down completely. These infinite curves in spacetime geometry represent the universe operating at its most extreme mathematical limits, where elegant equations predict physical conditions beyond human comprehension. The curvature of spacetime arises from Einstein's fundamental insight that gravity is not a force, but the manifestation of curved geometry. Massive objects create depressions in the fabric of spacetime, much like a heavy ball placed on a stretched rubber sheet. However, this analogy fails to capture the true extremity of black hole curvature, where the depression becomes infinitely deep. Dr. Roger Penrose from Oxford University, Nobel laureate whose work elucidated black hole formation, explains that black holes represent spacetime curvature so extreme that the geometry itself becomes singular, points where the mathematical description of spacetime breaks down and curvature approaches infinity, suggesting that general relativity reaches its fundamental limits. The mathematical description involves the Riemann curvature tensor, which quantifies how spacetime deviates from flat Euclidean geometry. For Schwarzschild black holes, specific components of this tensor diverge to infinity at the central singularity, while remaining finite but extreme at the event horizon. The scalar curvature R, which provides a measure of overall geometric distortion, approaches infinity as R approaches zero. The practical consequences of infinite curvature manifest through tidal forces that stretch and compress matter in ways that defy everyday physics. Near the central singularity of a stellar mass black hole, tidal accelerations exceed yp meters per second squared, millions of times stronger than Earth's surface gravity. These forces operate over such short distances that they can tear apart atomic nuclei. Consider what happens to the geometry of space itself near a black hole. The circumference to radius ratio, which equals 2 pi in flat space, becomes increasingly distorted as gravitational fields strengthen. At the event horizon, this geometric relationship breaks down completely. The spatial geometry becomes so curved that normal concepts of distance lose their meaning. Dr. Kip Thorne's calculations revealed that approaching the event horizon creates spatial distortions where radial distances become infinitely stretched compared to tangential distances. A meter stick pointing toward the black hole's center would appear infinitely long to distant observers, while maintaining its normal length in the local reference frame of someone falling with it. The temporal curves become even more extreme. Time dilation near black holes follows hyperbolic functions that approach vertical asymptotes at the event horizon. The mathematical relationship T_infinity equals T underscore local times square root 1 RSR reveals that as R approaches the Schwarzschild radius Rs, the denominator approaches zero, causing the time dilation factor to approach infinity. This mathematical infinity has profound physical implications. It means that processes occurring near the event horizon appear to take infinite time when observed from safe distances. A clock falling toward a black hole would appear to tick slower and slower, with the interval between ticks approaching infinity as the clock nears the event horizon. The concept of geodesics, the straightest possible paths through curved spacetime, becomes bizarre near black holes. What appears as straight-line motion in the local reference frame corresponds to extreme curves in the global spacetime geometry. Photons traveling on null geodesics near black holes follow paths that can spiral around the event horizon multiple times before either escaping or falling in. Dr. Subramanian Chandrasekhar, whose work on stellar evolution earned him a Nobel Prize, described black hole geodesics as the universe's ultimate demonstration of how extreme curvature can transform the simplest motion into complex trajectories that challenge our geometric intuition while remaining mathematically precise. The photon sphere, located at 1.5 times the Schwarzschild radius for non-rotating black holes, represents a region where spacetime curvature allows photons to orbit the black hole in circular paths. This creates an unstable equilibrium where light can theoretically circle the black hole forever, creating a geometric impossibility where straight-line motion becomes circular. The innermost stable circular orbit, ISCO, for massive particles occurs at 3 times the Schwarzschild radius, representing the closest distance where matter can maintain circular orbits around a black hole. Inside this radius, spacetime curvature becomes so extreme that stable circular motion becomes impossible, and all trajectories inevitably lead toward the event horizon. These geometric extremes create observational signatures that confirm Einstein's predictions. The shadows of black holes, first imaged by the Event Horizon Telescope in 2019, reveal the effects of extreme spacetime curvature on light propagation. The observed shadow of M87, a central black hole, matches theoretical predictions for how infinite curvature affects photon trajectories. The mathematical infinities in black hole spacetime aren't merely abstract. They represent physical conditions where the normal rules of geometry break down. The Weyl curvature tensor, which describes tidal effects, diverges at the central singularity, indicating that the geometric structure of spacetime itself becomes undefined. Frame-dragging effects near rotating black holes add another dimension to spacetime curvature. The lens-thirring effect causes the geometry of spacetime to twist around rapidly spinning black holes, creating regions where the distinction between space and time coordinates becomes arbitrary. This geometric mixing reaches extreme values near the ergosphere of maximally rotating Kerr black holes. The ergosphere represents a region outside the event horizon where spacetime curvature becomes so extreme that nothing can remain stationary relative to distant observers. The geometry itself is dragged around the black hole at such velocities that maintaining position requires faster-than-light motion relative to the local spacetime fabric. Dr. Roy Kerr, whose solution to Einstein's equations describes rotating black holes, notes that the ergosphere demonstrates how extreme mass energy can create geometric conditions where the very concepts of stationary and moving lose their usual meanings, revealing spacetime as a dynamic curved manifold, rather than a passive stage for physical events. The mathematical description of these infinite curves requires sophisticated differential geometry techniques. The Einstein tensor G, which describes spacetime curvature, must equal the stress-energy tensor T multiplied by Einstein's gravitational constant. Near black holes, both tensors approach extreme values that challenge numerical computation methods. The singularity theorems proved by Penrose and Stephen Hawking demonstrate that infinite curvature is not just possible but inevitable under general conditions. These theorems show that spacetime curvature must become infinite whenever matter collapses beyond a critical density threshold, suggesting that geometric infinities represent fundamental features of general relativity rather than mathematical artifacts. The information geometry near black holes creates additional paradoxes. As spacetime curvature approaches infinity, the geometric relationships that define information storage and transmission break down. This suggests that black holes may represent fundamental limits not just for matter and energy, but for information itself. The curvature coupling between matter and spacetime becomes self-reinforcing near black holes. Extreme curvature affects the motion of matter, which in turn affects the curvature through Einstein's field equations. This creates feedback loops where small perturbations can lead to dramatic changes in the geometric structure. These infinite curves in spacetime reveal the universe's capacity for geometric impossibilities that nonetheless follow precise mathematical laws. As we explore the event horizon itself, we'll discover how these mathematical infinities create physical boundaries that separate the knowable universe from regions where spacetime, geometry, becomes fundamentally undefined. Chapter 3. Event Horizons. The event horizon represents the universe's ultimate boundary, a mathematical surface where spacetime curvature creates a point of no return beyond which information cannot escape to reach external observers. This boundary exists not as a physical membrane, but as a geometric feature of severely curved spacetime where the normal relationship between cause and effect breaks down completely. The term event horizon was coined by physicist Wolfgang Rindler in the 1950s to describe the boundary beyond which events cannot influence distant observers. For black holes, this boundary occurs at the Schwarzschild radius Rs equals 2 gm per c squared, where the escape velocity equals the speed of light. Nothing, not even electromagnetic radiation, can travel fast enough to escape from within this geometric prison. Dr. John Wheeler, who popularized the term black hole in 1967, described event horizons as the cosmic censorship boundary where spacetime protects the rest of the universe from witnessing the impossible physical conditions that develop during gravitational collapse. The horizon ensures that singularities remain hidden from external observation. The formation of event horizons during stellar collapse represents one of nature's most dramatic phase transitions. When a massive star's core collapses beyond the Chandrasekhar limit, gravitational contraction becomes irreversible. The event horizon forms instantly when the collapsing matter reaches the critical density threshold, creating a boundary that grows outward at the speed of light. From the perspective of distant observers, this formation process appears frozen in time. The collapse appears to slow down dramatically as it approaches the would-be event horizon, with the stellar surface appearing to hover just outside the Schwarzschild radius forever. The material appears increasingly redshifted and dimmed until it fades from view, leaving behind a frozen star that never quite completes its collapse. However, from the perspective of the collapsing matter itself, the event horizon formation occurs in finite proper time. The infalling material passes through the Schwarzschild surface without experiencing any local discontinuity. There is no barrier, no membrane, no physical obstruction. The event horizon exists only as a global feature of the spacetime geometry, invisible to local observers. Dr. Saul Tucholsky from Cornell University, whose research addresses black hole perturbations, explains that the event horizon represents a null hypersurface in spacetime, a three-dimensional boundary swept out by light rays that are permanently trapped at the critical radius. These rays neither fall into the black hole nor escape to infinity, but remain perpetually suspended at the horizon. The mathematical definition involves light cones, geometric constructions that represent the possible paths light can follow through spacetime from any given event. At the event horizon, the light cones tip over so drastically that both forward and backward pointing light rays aim toward the black hole's interior. This geometric tilting ensures that nothing inside the horizon can send signals to the external universe. The coordinate systems used to describe event horizons reveal their subtle nature. Schwarzschild coordinates, commonly used for static black holes, show the event horizon as a genuine boundary where time dilation becomes infinite. However, Eddington-Finkelstein coordinates reveal that the horizon is merely a coordinate artifact. Infalling matter passes through smoothly, without encountering any physical barrier. The temperature and entropy properties of event horizons suggest they possess thermodynamic characteristics, despite being geometric features rather than material objects. Stephen Hawking's calculations revealed that black holes emit thermal radiation at a temperature inversely proportional to their mass. T equals p cubed 8 dmCb, whereas the reduced Planck constant and Kb is Boltzmann's constant. For stellar mass black holes, this Hawking temperature is extraordinarily small, roughly 10 to 7 Kelvin for a solar mass black hole. The entropy of black holes, calculated by Jacob Bekenstein and Hawking, equals 1/4 the event horizon's area measured in Planck units. S equals A4LP squared, where LP represents the Planck length. This relationship suggests that event horizons somehow encode information about the matter that formed them, leading to profound puzzles about information conservation in quantum mechanics. The Noether theorem, proved by Werner Israel and others, states that black hole event horizons are characterized by only three properties: mass, electric charge, and angular momentum. All other information about the matter that formed the black hole appears to be lost behind the event horizon, creating the famous black hole information paradox. Dr. Leonard Susskind's holographic principle suggests that all information about a black hole's interior is actually encoded on its event horizon surface. This radical proposal implies that the three-dimensional interior space is somehow equivalent to information patterns on the two-dimensional boundary, challenging conventional understanding of spatial dimensions. The dynamics of event horizons during black hole mergers reveal their malleable nature. When two black holes spiral together, Their individual event horizons merge smoothly into a single, larger horizon through a process that resembles soap bubbles combining. The final event horizon area always exceeds the sum of the initial horizon areas, confirming Hawking's area theorem. Rotating black holes possess more complex horizon structures. The Kerr metric describes black holes with angular momentum, creating an outer event horizon and an inner Cauchy horizon. Between these boundaries lies the ergosphere, a region where spacetime itself is dragged around the black hole so rapidly that remaining stationary becomes impossible. The Cauchy horizon represents a theoretical boundary where the predictive power of general relativity breaks down. Beyond this inner horizon, the spacetime geometry becomes unstable to perturbations, potentially creating closed time-like curves and other violations of causality. Most physicists believe quantum effects prevent the Cauchy horizon from forming in realistic black holes. The membrane paradigm, developed by Kip Thorne and colleagues, treats event horizons as if they were physical membranes with specific properties like electrical conductivity and viscosity. While the horizon is actually empty space, this mathematical approach simplifies calculations of black hole interactions with surrounding matter and electromagnetic fields. The observational signatures of event horizons come primarily through their effects on surrounding matter. As material falls toward a black hole, it forms an accretion disk that becomes extremely hot due to viscous heating. The innermost stable circular orbit marks the point where matter makes its final plunge toward the event horizon, creating distinctive spectral signatures. The Event Horizon Telescope, as direct imaging of black hole shadows, confirms the existence of event horizons as predicted by general relativity. The shadow represents the photosphere's projection on the sky, a region where light rays orbit the black hole or fall through the event horizon rather than escaping to distant observers. The firewall paradox, proposed by Ahmed Almheri and colleagues, suggests that event horizons might not be the benign boundaries that general relativity predicts. If information is encoded on the horizon surface, then infalling observers might encounter a firewall of high-energy radiation at the horizon, contradicting the equivalence principle. The quantum nature of event horizons remains deeply mysterious. Hawking radiation suggests that quantum fluctuations near the horizon create particle pairs, with one member falling through the horizon while the other escapes. This process gradually evaporates the black hole while potentially destroying information, creating fundamental conflicts between general relativity and quantum mechanics. The formation mechanisms for supermassive black holes with masses exceeding billions of suns remain unclear. Their event horizons are enormous. The horizon radius of a billion solar mass black hole exceeds the orbit of Neptune. These gentle giants create relatively weak tidal forces at their event horizons, allowing extended objects to cross the boundary intact. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that naked singularities, regions of infinite spacetime curvature, not hidden behind event horizons, cannot form in realistic gravitational collapse scenarios. Event horizons thus serve as cosmic protection, ensuring that the universe's most extreme physics remains hidden from external observation. As we explore the experience of falling through these cosmic boundaries, we'll discover how the journey toward infinite time dilation transforms the relationship between observer and observed, revealing the profoundly relative nature of time itself. Chapter 4. Falling Forever. The experience of falling into a black hole represents the ultimate journey into spacetime's most extreme conditions, where the infalling observer encounters physics that defies everyday comprehension, while distant observers witness a cosmic drama that appears to unfold over infinite time. This dual perspective reveals the profoundly relative nature of temporal experience in curved spacetime. From the moment an observer begins falling toward a black hole, their experience diverges dramatically from what external observers witness. The falling observer feels nothing unusual initially. They are in free fall, experiencing weightlessness just like an astronaut orbiting Earth. Einstein's equivalence principle ensures that gravitational acceleration feels identical to being in an inertial reference frame far from any gravitating body. Dr. David Finkelstein from Georgia Tech, whose work on black hole interiors revolutionized the field, described the infall experience as the ultimate demonstration of general relativity as principle that there are no preferred reference frames. The falling observer experiences normal physics throughout their journey, while external observers witness time dilation effects that approach mathematical impossibility. As the falling observer approaches the event horizon, tidal effects begin to manifest. For stellar mass black holes, these tidal forces become extreme well before reaching the horizon. The gravitational gradient between the observer's head and feet creates differential accelerations that stretch the body radially while compressing it tangentially, the notorious spaghettification effect. The mathematics of tidal acceleration reveal the physical impossibility of surviving the approach to stellar mass black holes. The tidal acceleration difference between 2 points separated by distance d is approximately delta A equals 2 Gambian delaces r cubed for a 10 solar mass black hole. This tidal acceleration exceeds Earth's surface gravity when the separation distance is just 1 meter and the radial distance is 100 kilometers, far outside the event horizon. The human body would be torn apart long before experiencing the extreme time dilation effects at the horizon itself. However, supermassive black holes present a completely different scenario. The gentle giants at galactic centers have event horizon radii measured in astronomical units, creating tidal gradients so mild that human-sized objects can cross the horizon intact. For the 4 million solar mass black hole at our galaxy center, tidal effects remain manageable until well inside the event horizon. The temporal experience during infall reveals general relativity's most counterintuitive predictions. From the falling observer's perspective, their wristwatch continues ticking normally throughout the journey. They experience no slowing of time, no stretching of moments into eternities. Their proper time proceeds at its usual rate, with the journey from horizon to central singularity taking finite time, perhaps minutes for stellar mass black holes. Meanwhile, distant observers witness a dramatically different sequence of events. As the falling observer approaches the event horizon, they appear to slow down progressively. Their movements become increasingly sluggish, their clocks run slower and slower, and light from their body becomes increasingly redshifted and dimmed. Dr. William Unruh from the University of British Columbia, whose work addresses observer-dependent phenomena in general relativity, explains that the falling observer's final moment, as viewed from infinity, is stretched across infinite time. The last photons emitted just before horizon crossing take infinite time to reach distant observers, creating the illusion that the fall never actually completes. The redshift effects become extreme during the final approach. Photons climbing out of the deepening gravitational well lose energy proportional to the gravitational potential difference. At the event horizon, the gravitational redshift approaches infinity, meaning that high-energy gamma rays emitted by the falling observer would be shifted to arbitrarily low frequencies by the time they reach distant observers. The information transmission properties during infall create paradoxes that challenge our understanding of causality. From the falling observer's perspective, they can send signals back to the external universe only until they cross the event horizon. After crossing, no information can escape, creating a fundamental communication barrier between the black hole interior and the external spacetime. The experience of crossing the event horizon itself holds special significance in general relativity. According to the equivalence principle, the falling observer should notice nothing special about this moment. It represents merely a coordinate boundary rather than a physical barrier. There should be no membrane to pierce, no discontinuous change in the local physics. However, recent theoretical work suggests this picture may be incomplete. The firewall paradox proposes that quantum effects might create a wall of high-energy radiation at the event horizon, contradicting the classical prediction of smooth horizon crossing. This would mean that falling observers encounter lethal radiation at the very moment they expect to experience normal spacetime geometry. The geodesic paths followed by unfolding matter reveal the geometric inevitability of the journey toward the central singularity. Once inside the event horizon, all time-like and null geodesics point toward the center of the black hole. The radial coordinate r becomes time-like inside the horizon, meaning that moving toward smaller r values becomes as inevitable as moving forward in time. Dr. Andrew Strominger from Harvard University, whose work addresses black hole thermodynamics and quantum gravity, notes that inside the event horizon, the roles of space and time coordinates exchange. The radial direction becomes temporal, while the time direction becomes spatial. This coordinate reversal reflects the profound geometric transformation that occurs when spacetime curvature exceeds critical values. The experience near the central singularity represents physics beyond the scope of general relativity. As the falling observer approaches r equals 0, tidal forces approach infinity and spacetime curvature becomes undefined. The classical theory predicts that the observer would be crushed to infinite density in finite proper time, experiencing forces that exceed any conceivable physical limit. The thermal atmosphere surrounding black holes adds another dimension to the infall experience. Hawking radiation creates a thermal bath of particles near the horizon, with temperatures that depend on the black hole's mass. For stellar mass black holes, this temperature is negligible, but for microscopic black holes, the thermal environment could be lethal. The quantum fluctuations near the horizon create particle pairs through vacuum polarization effects. These virtual particles become real when separated by the horizon, with one member falling into the black hole while the other escapes as Hawking radiation. The falling observer would witness enhanced quantum activity as they approach the horizon. The measurement paradoxes during infall reveal fundamental tensions between general relativity and quantum mechanics. If information is conserved, then the falling observer's quantum state must somehow be preserved despite apparently disappearing behind the event horizon. Various proposals, including the holographic principle and black hole complementarity, attempt to resolve these contradictions. The cosmic time perspective adds yet another layer to the infall experience. As the falling observer approaches the horizon, they witness the accelerated evolution of the external universe. Due to gravitational time dilation effects, the universe's future history unfolds in their reference frame over relatively short proper times. This means that falling observers could theoretically witness the far future of cosmic evolution, including the eventual evaporation of their host black hole through Hawking radiation. From their perspective, they might see the black hole shrink and disappear while they continue falling toward what was once its center, a paradox that highlights the complex interplay between different reference frames in general relativity. The journey into a black hole ultimately represents the universe's most extreme test of physical law. The falling observer experiences conditions where general relativity approaches its theoretical limits while quantum effects become dominant. Their experience bridges the gap between classical spacetime geometry and quantum gravity, providing a natural laboratory for testing theories that unify Einstein's curved spacetime with quantum field theory. As we delve into the mathematical framework that predicts these impossible temporal effects, we'll discover how Einstein's field equations generate infinities that challenge our understanding of what mathematics can reveal about physical reality. Chapter 5. Mathematical Infinity. The mathematics of black hole spacetime generate infinities so extreme they challenge the very foundations of physics, revealing regions where Einstein's elegant equations predict values that exceed any finite number while maintaining mathematical consistency. These mathematical infinities represent more than abstract curiosities. They point toward physical conditions where our current theories reach their fundamental limits. The Schwarzschild metric, Carl Schwarzschild's solution to Einstein's field equations, contains the seeds of mathematical infinity embedded within its elegant structure. ds equals 1 twog mrc, dt plus 1 twog mrc, y dr squared plus r squared, d plus sind. As the radial coordinate r approaches the Schwarzschild radius rs equals 2 gm per c squared, the metric coefficients approach singular values. The time component approaches 0 while the radial component approaches infinity, creating coordinate singularities that initially puzzled physicists. Dr. David Hilbert, who independently discovered the Schwarzschild solution, recognized that these mathematical infinities revealed profound features of spacetime geometry rather than mere computational artifacts. He wrote that the infinities appearing in gravitational field equations represent nature's way of indicating where the geometric description of spacetime itself becomes fundamentally altered. The curvature scalars constructed from the Riemann tensor provide more invariant measures of spacetime geometry near black holes. The Kretschmann scalar K equals RAGGCR, which measures squared curvature, approaches finite values at the event horizon, but diverges to true infinity at the central singularity, K equals 48G squared MDR, YC. This mathematical relationship reveals that curvature grows without bound as R approaches 0, indicating genuine geometric pathology rather than coordinate-dependent artifacts. The physical spacetime itself becomes infinitely curved at the black hole's center. The Weyl tensor, which describes tidal gravitational effects independent of matter distribution, exhibits even more dramatic infinities. For Schwarzschild black holes, components of the Weyl tensor approach infinity as R, creating tidal forces that would stretch any material object to infinite length while compressing it to 0 thickness. Dr. Roger Penrose's singularity theorems proved that these mathematical infinities are inevitable consequences of general relativity under broad physical conditions. The theorems demonstrate that spacetime curvature must become infinite whenever matter collapses, beyond critical density thresholds, regardless of symmetries or initial conditions. The mathematical treatment of infinity requires sophisticated analytical techniques. The concept of asymptotic behavior describes how physical quantities approach infinite values, while limiting processes reveal the mathematical structure underlying these divergences. Near black hole singularities, most physical quantities follow power law relationships that approach infinity at well-defined rates. The coordinate singularities and event horizons represent a different type of mathematical infinity, one that can be removed through coordinate transformations. Eddington-Finkelstein coordinates eliminate the apparent infinity in the Schwarzschild metric at R equals Rs, revealing the event horizon as a regular boundary in appropriately chosen coordinate systems. However, the central singularity presents a true geometric infinity that cannot be eliminated through coordinate choices. At R equals 0, the spacetime manifold itself becomes undefined. There is no coordinate system that can render the curvature finite. This represents a fundamental breakdown of general relativity's predictive power. The mathematical infinity of time dilation creates paradoxes that challenge conventional understanding of temporal relationships. The time dilation factor, 1 RSR minus 1/2, approaches infinity as R approaches Rs, meaning that finite proper time intervals correspond to infinite coordinate time intervals for distant observers. Consider the mathematical implications. If tau represents proper time for an infalling observer and t represents coordinate time for distant observers, then dTd equals 1 RSR, 1/2. As R gives Rs, this ratio approaches infinity, meaning that the last few seconds of the infalling observer's experience before crossing the Horizon correspond to infinite time as measured by external observers. The integration of this relationship reveals that the total coordinate time required for an observer to reach the event horizon from any finite distance is infinite. Integral arch to rs dt doctor ddt tau equals infinity. This mathematical result demonstrates that horizon crossing requires infinite time from external perspectives, creating the frozen star appearance observed by distant viewers. The mathematics of rotating black holes introduce additional infinities through the Kerr metric. For maximally rotating black holes, the ring singularity at the equatorial plane creates regions where spacetime curvature approaches infinity along closed curves rather than at isolated points. The mathematics predict that these ring singularities might serve as gateways to other regions of spacetime. The ergosphere of Kerr black holes generates mathematical infinities in the frame-dragging terms. The angular velocity of spacetime dragging approaches the rotation frequency of the black hole itself, creating regions where maintaining stationary positions requires infinite energy from the perspective of distant observers. Dr. Subramanian Chandrasekhar's mathematical analysis of Kerr black holes revealed that the equations governing particle motion near rotating black holes can exhibit chaotic behavior near the ring singularity. Small changes in initial conditions lead to vastly different trajectories, suggesting that the mathematical infinities introduce fundamental unpredictability. The quantum field theory treatment of black holes introduces additional mathematical infinities through Hawking radiation calculations. The stress-energy tensor for quantum fields in curved spacetime develops infinite expectation values at the event horizon, requiring sophisticated renormalization techniques to extract physically meaningful results. The path integral formulation of quantum gravity near black holes involves summations over infinite numbers of spacetime geometries, each weighted by the Einstein-Hilbert action. These infinite sums often diverge, requiring regularization procedures that highlight the mathematical complexity of quantum gravity near singularities. The holographic principle attempts to resolve some mathematical infinities by mapping the infinite-dimensional Hilbert space of the black hole interior onto the finite-dimensional boundary at infinity. This correspondence suggests that apparent infinities in the bulk spacetime correspond to finite information content on holographic screens. The ADS-CFT correspondence provides a mathematical framework for understanding these holographic relationships. The infinite redshift surfaces near black hole horizons correspond to the UV cutoff scales in the dual conformal field theory, suggesting that mathematical infinities encode information about high-energy physics. The mathematical treatment of black hole thermodynamics reveals infinities in the partition function calculations. The entropy of black holes proportional to horizon area can approach infinite values for sufficiently large black holes, creating thermodynamic systems with infinite heat capacity and other unusual properties. The renormalization group flow near black hole horizons shows how mathematical infinities arise from the interaction between different energy scales. High-energy quantum fluctuations near the horizon create divergences that must be systematically removed to obtain finite physical predictions. The information paradox emerges from mathematical infinities in the quantum state counting. If black holes evaporate completely through Hawking radiation, the infinite-dimensional Hilbert space of possible internal states must somehow be encoded in the finite number of Hawking photons emitted during evaporation. The mathematical structure of these infinities suggests that new physics beyond general relativity becomes essential near black hole singularities. String theory, loop quantum gravity, and other quantum gravity approaches attempt to resolve these infinities by modifying the mathematical framework at Planck scales. The asymptotic safety program proposes that gravitational interactions approach a fixed point at high energies. potentially taming the mathematical infinities through non-perturbative effects. This approach suggests that spacetime itself might have a discrete structure at the smallest scales, eliminating true geometric singularities. The mathematics of black hole infinities ultimately reveal the boundaries of our current theoretical understanding. These mathematical divergences point toward new physics that must emerge when quantum effects become comparable to gravitational effects, suggesting that the universe's most extreme conditions require mathematical frameworks beyond classical general relativity. Chapter 6: Observational Evidence. The theoretical predictions of extreme time dilation near black holes have been confirmed through decades of increasingly sophisticated observations that reveal the universe's most extreme temporal effects in action. These observations transform abstract mathematical predictions into measurable phenomena that demonstrate how gravity literally controls the flow of time itself. The first observational evidence for gravitational time dilation came from precision measurements in Earth's gravitational field. The Pound-Rebka experiment of 1959 used the Mossbauer effect to measure the gravitational redshift of gamma rays traveling vertically in Harvard University's Jefferson Tower. Despite the minuscule height difference of 22.5 meters, they detected the predicted frequency shift of 2.5 times 10 to 15, confirming Einstein's prediction to within 1%. Dr. Robert Pound and Glenn Rebka's groundbreaking measurement demonstrated that even Earth's relatively weak gravitational field produces measurable time dilation effects. Pound later reflected that this experiment proved that gravity affects the rate of clocks in exactly the manner Einstein predicted, providing the first laboratory confirmation of one of general relativity's most counterintuitive consequences. The global positioning system provides continuous real-world confirmation of gravitational time dilation effects. GPS satellites orbit at altitudes where Earth's gravitational field is approximately 0.18% weaker than at the surface, causing their atomic clocks to run faster by 45 microseconds per day. Without corrections for this time dilation, GPS accuracy would degrade by several kilometers daily. Dr. Neil Ashby from the University of Colorado, who developed the relativistic corrections essential for GPS accuracy, explains that every GPS calculation performed billions of times daily confirms Einstein's predictions about time dilation. The system represents a practical demonstration that relativity is not just abstract theory, but essential technology. The observation of binary pulsars provided the first indirect evidence for extreme gravitational effects in strong field regimes. The Hulse-Taylor binary pulsar PSRB1 913+16 consists of two neutron stars orbiting each other with orbital velocities reaching 0.1% the speed of light. Precision timing measurements reveal relativistic effects including time dilation, orbital decay from gravitational wave emission, and perihelion precession. The orbital decay rate of the Hulse-Taylor pulsar matches Einstein's predictions to within 0.2%, providing extraordinary confirmation of general relativity in the strong field regime. Dr. Russell Hulse and Joseph Taylor received the 1993 Nobel Prize for this discovery, which demonstrated that neutron stars create gravitational fields strong enough to produce easily measurable relativistic effects. Direct observations of matter approaching black holes reveal extreme time dilation effects through spectroscopic analysis. The X-ray emission lines from iron atoms in accretion disks around black holes show dramatic gravitational redshifts that increase toward the inner edge of the disk. These observations confirm that time dilation approaches extreme values near black hole event horizons. The new STAR and X-MEM-Newton X-ray telescopes have measured iron K-alpha emission lines from accretion disks with redshifts corresponding to gravitational time dilation factors exceeding 10. These observations probe regions where spacetime is so curved that time flows 10 times slower than in weak gravitational fields. Dr. Andrew Fabian from Cambridge University, whose team pioneered these X-ray spectroscopy techniques, notes that we can literally watch time slowing down near black holes by measuring how gravitational fields redshift the atomic emission lines from infalling matter. The observations match Einstein's predictions with remarkable precision.